Okay, welcome back. So welcome back to having a look at a further use of domains. This is part 3. So determine the domain of 10 minus the square root of x. Well, you know what? I don't know anything about the square root of x. We've only just learned about linears, linears and quadratics. And you did a little treaty on E and ln. Ln was coming up like this. So really, what's the square root of x look like? I don't know what it looks like. Well, let's go and have a look. Let's see what we can see with the square root of x. Use a bracket. And really, the square root of x shouldn't be that complicated. Oh, look. It's got a lovely swoop up with test values. We'll draw that graph, testing values. So that's a nice way to do it. So the square root of x looks like this. Nice big swirl up. So that means it's got a domain. It takes all the x values, including zeros. So it's allowed to have zeros, and it's evident. So it's allowed to have zeros. So 0 makes sense in there. Zeros, okay. All right. So what happens if we get 6x? I'd like to see that on there. Oh, let's do it together. Let's do the square root of 6x. And we'll go common. And this time we'll write 6x. Video is just processed for me. And let's see what that does. Now, this might not like it. It's plotted it for us, so that's good. 6x now. 6x. It's taken the square root of 6 out using maths techniques. So it's the orange one. Oh, look, it's made it steeper. That's like the shapedness of our linears. So we made steeper linears by interfering with y equals mx plus b. M changed. Y equals ax squared plus bx squared plus c, etc. The steepness and the shape upside down. Y equals e to the x, y equals 2 to the e to the 2x, e to the 4x. I didn't do that, but we'll have to do that. So 6x is steeper. Steeper than our little friend over here. Okay. What about if we do x minus 2? What happens if we do x minus 2? And I'm just going to help Wolfram out here. I don't want it to tell me about its exact result, so I'm going to tell it to plot. And this time I want to put in x square root of x minus 1. I want to see what that looks like. X minus 1. Let's see what those three graphs look like. What does minus 1 do? Oh, look what it did. It shifted it to 1. Hey, that's the way that we shift quadratics and linears. We have a shifter. So the shifting mechanism is working for all of these types of curves. Oh, well, that's pretty interesting to know. So if I put a minus in, it shifts it to a plus. Well, I wonder what this one is then. 10 minus 2x. But before I go and do that, I want to just explore this a little bit further. We might be able to come up with some common sense about this. 0 is okay. So we're going to take this bit out and treat it with an inequality. We're going to say 10 minus 2x, 0 is included. So can you tell us what the x values are, please? So we can go ahead and do all of this. So we can add 2x or leave the x on the left-hand side. So this time we'll just subtract 10 minus 2x. Okay, we're going to divide by minus 2 now. Oops. So alarm bells, dividing by something that's negative. So this will be divided by, so over here we'll have x, because they'll cancel. Minus and a minus make a plus. 10 on 2 is 5. So it's not going to be the same here. Look, it's going to change, so be careful. Reversing, that's the rule. Not convenience, the rule. So x is less than 5. So in this particular case, we will get anything, any x value in conjunction with the 10 minus 2x, in conjunction with that, that'll be 0 or positive if x is less than or equal to 5. So that's quite a mouthful. If x is less than or equal to 5. So we can say, therefore, the domain is x is less than or equal to 5. I'd still like to have a look at that on the plot, though, wouldn't you? So 10 minus 2x. So do you think we could have a 10 minus 2x, please? The square root of 10 minus 2x. Okay, and let's see what you've got. Let's see what you've got. There's your final one. Oh, look at this 10 minus 2x. It's this one down here. It's this darker tanny colour. Oh, there it is there. Look, going all the way across. So it's been shifted, hasn't it? It's been shifted and it's a bit steeper. Certainly a bit steeper than these laying down ones. So it's steeper and it's been shifted all the way. So that's something that we'd like to increase the plot there. I'd like to increase the plot. So what I'm going to do is I'm going to ask it and say, listen, do you think you could do x from, say, minus 1 to 10? Do you reckon we can have a look at that plot? X from minus 1.5 to 10. Oh, there, look at that. So the shift has gone all the way. Oh, 5. 5, okay. So that's why we got x equals 5, because 5 shows us. And the negative's made it switch around, hasn't it? The minus 2x has made it change direction. So we're used to all of our curves being changed by the coefficients. And while it's a bit steeper, it's also changing direction. So look at that, it's asymptotic to 5 now. Oh, wow, isn't that fantastic? All right, so if we just put in the value without the plot command, it will give us all the domain and range details that you can have. All right, so if I were to put in this one here just by itself, and I don't know if I could do that, can I? Copy. Can you copy the tab? Probably wasting time. Let's do Wolfie for us. And in the box I can put the value that I'm interested in. And just looking at it as an entity, what does that look like as an entity? And so we can clearly see that x is 5 and the domain is x is less than or equal to 5. So it's showing us the shifting nature. Alright, so this encyclopedic discovery tool is very important for you guys to practice, to grow and develop your sense of knowledge. It's not just about the written paper, it's also about the fact that you want to test that, don't you? Minus x. You'd like to see what would happen if we did a minus 2x. Okay, I'd like to see that too. What would happen if we did a minus x? Because I thought we said we couldn't have a minus x. What would happen in that case? So it's treating it like a minus x. See, it's just doing that. So that's something new for us to understand, that it's changing it around. Okay, so the negative x. So we just learn about these things as we go and do some discovery, and that's our domain. So we've got that sorted out. All right, so let's use that lens to think about this guy here. What's the two ideas then? Well, we know that 0 is okay. 0 is okay. But what else do we know? What can't we have? We can't have a 0, can we? We can't have that. That's undefined. That's a very big analysis idea. Any quotient that's got your calculator will throw up an error. Undefined. So we can't have a quotient that's 0. So what we're going to do is we're going to take this bit here and we're going to say, listen, this time when we do this, we want you to be positive only. We won't have any zeros on the denominator because we know the square root will kick up a 0. That's okay. But 1 over 0, that's no good. So even though the square root will kick a 0 up without any problem, we don't want it to be 0 because we want it to be positive, because we can't have a quotient. So all we're doing now is just working on this. So we can subtract 3, minus 4x is greater than minus 3. Divide through by minus 4. Be careful now. That's the rule. Minus and a minus is a plus. And minus and a minus is a plus, so it's 3/4. But what have we got to do? change it. So it's not the convenience one, it's the rule. Okay, so this now represents the domain. This is the domain of this function. It's throwing up a positive. And of course we can plot that. That's going to be a composite plot, so it's going to be a bit fierce and a bit sophisticated. It's going to be our one of these, but inverted. It'll be 1 over the reciprocal, so that's going to take a bit of a mind stretch to get. But in this case here, I'm not bothered by that. So, all right, let's keep looking at how we might progress these. What have we got here? So we can do an end. So our domain is going to be dependent on that one. So x minus 2 is greater than 0. So x minus 2 is greater than or equal to 0. We can have a 0. All right, so it's a composite domain. And the other one we want is 12 minus 3x is greater than, but it can be 0. There's no quotients there, it's just the square root signs. Okay, so if we do the operations on there, we'll add 2 to both sides, so x will be greater than or equal to 2. And if we do the same thing here, processing this, being a bit naughty, Jason, minus 12 minus 3, so x will be minus 12 divided by minus 3 is 4. But what do we need to do? Because we divided by minus 3, you have to do the work. Jason, no, you have to do the work, please. You do the work, okay? You do the work and show yourself that that's what's required, okay? So we're going to put those together as an end function, okay, because it's a piecemeal domain. This bracket here, it means that this is a piecemeal domain. So we're going to rely on the fact that both of those domains are in play. So if we do the convenience thing and turn this one around, it'll be 2 for the convenience. It's less than x. Now we can put them together. So we'll have 2 is less than x and x is less than 4. So we build the intersection. Okay, so we've used AND to help us build the intersection. So this represents an interval, an inclusive interval of 2 and 4. Okay, so this interval is the interval over which these requirements are met, and so we've been able to process the function in a sensible way. That is without negative values underneath the square root sign. Okay, so very good. All right, let's move on to the next couple. So in this case here, this will be a little bit tricky, won't it? Because what we're looking to do is, y values are all less than minus 3x minus 7. Now that looks familiar, doesn't it? Minus 3x minus 7. That looks like a graph. Okay, so let's graph that. Minus 3x minus 7. Minus 7 will be down here. Minus x will be like this, so it's 3 times as steep. Okay, and it means also that because it's been shifted, it's going something like this. 3 times as steep. Minus 3. Now, we have to interpret this. Y is less than. So the first time, we need to think about what values of y are below the function. So these are our y values and our x values. What values of y are below the function? Because the function is defining a boundary. So even though these are y values that are occurring here, what we understand is that this side is the region or the graph. So let's put that in and see what we can't do with that. So y is less than, and you put the equal sign after, minus 3x. And we could put some values in, but we've got technology to help us, so GeoGebra or Wolfram Alpha or whatever it is that you want to use, Maple or any of those particular things can be helpful. So what it's saying is, there's our line, and there's the region below it. Okay, so I just want to plot that, see what it does. Put that plotty. I don't want plotty. I want that one. So there's the same graph. So it's showing that everything that's happening with, even though y values are going up and down, it's all the y values that are on the below side. Okay, so it's the lower side. So they're all those values there. Okay, so we can draw that out like that as a region. All of those values of y that as a result of being plotted are less than. Okay, less than or equal to. Now just notice that because it's got this one, I've made a solid line. I'm going to make a distinction about that. So in this case here, 5x plus 1, 5x plus 1, so it's a shifter up to 1, and 5x is quite a bit steeper, isn't it? So not more steep than 3x, so it's even more steep. Like that, 5x plus 1. Okay? Now, this time, I'm going to rub that out. Because this time, I want to make the distinction that it's a dotted line. Why am I doing a dotted line? Because the function values themselves, as defined, are not included. So the convention is that we draw a dot. Okay? So what are all the y values that are greater than that one? Okay, what are all the y values that are greater than that line? Okay, so up we go. So that kind of thing is very tricky. And so you can put that in, 5 is less than, y is less than 5x plus 1. And just to check that you're making all that sense there. So there's our values and all of the ones that are y is greater than the function values. So y is greater than the function values. Okay, same kind of graph, y is greater than the function values. Alright, so the next one is 5 minus 2x. 5y minus 2x. So what are we thinking about that? Again, it's not in the right form, is it? It's in general form. This is in general form. Okay, so the general form needs to be modified so that we can have y. So we've got to do a bit of pre-work to understand what that means. Okay, so we would add 2x. What you do to one side, you do to the other. So 5y would be greater than 2x plus 9. Now that's more looking like it. Divided by 5. Be careful, split the fraction. So y is now equal to 2/5 x plus 9. So that's the one we're looking for. Okay, that's the one we're looking for. So 2/5 x are very droopy. Okay, 2/5 x is very droopy. And 2x is steep. 2x is steep. And so what we'll end up with is a shifter at 9 on 5, which is 1 and 4. So 1 and 4/5, which is 9 on 5. Okay, that's this value here at 0. And also, I'm just putting the mixed fraction as an equivalent there. It's 2/5 steep. So instead of being like this, it's sleepier. Okay, so I'll extend this out a little bit to recognise that. So it's 20%. So it's really just, now it's inclusive, so I can do the solid line. Do the solid line, let that go off there like that. Okay, so there's our value. We can work that out as well if we need to. But y is greater than that line. So y is greater than that line. There you go. Y is greater than that line. So that's fairly straight. Alright, so we found that we can use inequalities very helpfully. And that's allowing us to use inequalities to help us do a bit of understanding of our functions, domain and range and the like, and sketching as well. Alright, I'll be back with the next part momentarily, and we will have a look at a different method for solving these kinds of problems.